Hi there, my name is Franky de Bruyne. Welcome to this channel on signals, systems and control. Today we'll talk about the Fourier series. So, what do we remember about the Fourier series? Well, I guess you remember that it's a decomposition of a periodic function into a sum of sines and cosines. I could add that we'll consider functions that are real valued. So the functions that we consider produce a real value as opposed to a complex value. The period of our function will be called t and it's expressed in seconds. Associated to this period we have the fundamental frequency omega 0, which is 2 pi over t and it's expressed in radians per second. This frequency intervenes in the sines and cosines. But of course, there are other frequencies that are coming in, these sines and cosines, and they are called the harmonics, right? So it's the fundamental frequency omega 0 multiplied by an integer k. So if k is equal to 2, we speak about harmonic 2. If k is equal to 3, harmonic 3, and so on. Well, that's not too bad for starters, but what is on the rest of the menu for today? Well, of course, we have to formalize all this. We have to obtain the so-called trigonometric Fourier series, the so-called exponential Fourier series. These are the two approaches that you'll encounter in the literature. And of course, we'll have to look at the links between these two Fourier series. And next, we'll look at interpretations, and the best way to do this is to use animations. Well, let us start with an animation, right? What we'll do is construct the function that is shown on the screen. Well, as you can see, the first term is C0, so that's a constant signal that will allow you to set, well, the average of the signal that you're creating. Well, the next terms in the sum are considering cosines and sines of increasing frequencies, starting from the fundamental frequency, this is k is equal to 1, and then considering harmonics 2 to 7. So the degrees of freedom here are the coefficients C0, the coefficients AK and BK, where k ranges from 1 to 7 in this case. Instead of working with cosines and sines, what we could do is work with shifted cosines. This is what you see in the second expression. Notice that we still have 2 degrees of freedom. In the first expression we have 2 coefficients, AK and BK. In the second expression we still have 2 degrees of freedom, DK and VK. We'll see later that you can produce the same functions using these two approaches. We've noticed that we need 2 degrees of freedom. So instead of working with AK, BK, DK or VK, we'll work with a complex number C of k that we'll call the Fourier coefficient. This complex number naturally includes these 2 degrees of freedom. If you write C of k under its polar form, the first degree of freedom is of course the modulus and the second one the argument of ck. If you write it under a Cartesian form, well, the first degree of freedom is the real part of ck and the second degree of freedom the imaginary part of ck. Well, in this first expression over here, we have replaced the degrees of freedom AK and BK by playing with the real part of CK and the imaginary part of CK. We will see later why we have this coefficient 2 over here, the coefficient 2 over here, and why we have here a minus sign. But here, to produce a function, you can play with the parameters C0, the real part of ck, and the imaginary part of ck, where k again ranges from 1 to 7. In this second expression, we have replaced the degrees of freedom dk and vk by playing with the modulus of ck and the argument of ck. This is the expression that you're playing, and we'll see later again why we have this coefficient 2. But again, the degrees of freedom are C0, the modulus of ck, the argument of ck, and this for k ranging from 1 to 7. Well, the 2 expressions over here can be shown to be equivalent. It's very easy if you remember the following trigonometric identity from your trigonometry classes. Well, if you use this trigonometric identity over here in the cosine, this being alpha and this being beta, this is what you produce, and this is actually the real part of ck. Remember, this was the polar expression of ck. If you rewrite this complex exponential as follows, right, you can clearly see that this is the real part of ck and the modulus times sine is the imaginary part of ck. So we have just shown that these two expressions here are completely equivalent if you work with these Fourier coefficients ck. So in our animation we'll work with this second expression. So in summary, we'll work with the Fourier coefficients. The Fourier coefficients are complex numbers, and we'll use here the polar expression. We define a fundamental frequency, omega 0, which is 2 pi over t. Another way to see this is that we work with a certain period, that is t. Well, we'll produce functions using this expression over here. C0 will allow us to shift the signal. Notice that in this sum here you have cosines over one or several periods. So if you take the average of this term over here, you'll have 0. So you'll be able to influence the mean, right, using C0. And then you have a certain number of terms here that corresponds to the fundamental frequency and to the harmonics 2 to 7, because in our example n is limited to 7. You can play with the amplitude of each individual cosine by using the modulus of the corresponding ck, and you can play with the phase shift of each individual cosine by playing with the argument of the corresponding Fourier coefficient. Well, each individual cosine here has a period of t over k, right? So if you sum these cosines, you'll have a function that will still be periodic of period t. We'll consider the period that is centered around t is equal to 0. So we'll consider the period where t lies in the interval minus t over 2, t over 2. Well, we can have a look at theta k here for each individual harmonic when t goes from minus t over 2 to t over 2. Well, this theta k here will go from this expression to this expression over here, and what is important to see is that this angle theta k will go around k times. This is important for later for the animations that consider phasors. And here is this first animation. As you can see, you can influence the 7 Fourier coefficients using sliders. You can influence the modulus of each individual Fourier coefficient, and you can also influence its argument. Right now in the animation, all coefficients are set to 0 except C1, which has a modulus of 0.5, and the argument of C1 is 0, which means that C1 here is a real number, right? You remember that in this sum, the modulus of C1 was multiplied by 2. This explains why you have here a cosine of amplitude 1, and it is not phase shifted because the argument of C1 is 0. You also have the coefficient C0 that allows you to shift the signal, as you can see, right? So here you have the mean, here you have the original harmonic 1 or fundamental cosine, and you can see that the sum will just shifts the signal. In the sequel, we'll work with C0 is equal to 0. You can also play with the parameter t. For the moment, the period is 1, and you can see that we're indeed, as you can see here in green, considering a period that is centered around t is equal to 0. So a period that goes from minus t over 2 to t over 2, here from minus 0.5 to 0.5. If you change the period over here, all this does is do some scaling. For instance, if t is smaller than 1, right, then it's compression, and if t is larger than 1, then it's exponential. In the sequel, we'll work with t is equal to 1. So what we can do now is start playing with those sliders, right? Well, of course, we can play with this one, and all this does is really do a phase shift of the fundamental cosine, right? You can start adding, for instance, a second harmonic, yeah? So here you have the fundamental frequency, here you have the harmonic frequency, and here you see the sum, right? And then you can start phase shifting this second harmonic, and you can obtain all kinds of shapes for the sum, right? You can do this for other harmonics, right? Yeah, so here you see the harmonic 3 appearing, here harmonic 4, and each time what you can do is really phase shift. And what you see is that you obtain the function in blue, which is the sum, and what you can see is that this function in blue remains periodic of period t. So here we're working with t is equal to 1 over here, and again we're considering this window centered around t is equal to 0. Well, if you're really patient, what you can do is play with the sliders until you obtain something that looks like really a square wave. Remember, the blue curve here is the sum of this C0 and this shifted cosines, right? And this suggests that if you would take more and more terms, well, you would be able to approximate this square wave better and better. Well, as you can see over here in the sum, there are only uneven harmonics. So this is corresponding to the fundamental frequency, the third harmonic, fifth harmonic, and seventh harmonic. And this you can see over here. You can see that the modulus of each even Fourier coefficient is 0 over here. So this explains why the even harmonics are not present over here. You can see also that all trigonometric functions are really sines, right? And this can be seen over here because the arguments of the uneven C case are minus pi, right? And a cosine that is being shifted by minus pi yields a sine, and this is indeed what you see over here. We can also have a look at the amplitude. Remember that the amplitude of a given harmonic, it's the module of the corresponding Fourier coefficient times 2. So for the fundamental frequency, the modulus of C1 is 0.64. So we have an amplitude that is 2 times 0.64, so 1.28. Here the amplitude is this one multiplied by 2, and so on. Well, remember that the square wave is an uneven function, so it makes sense if you're trying to decompose it, that you decompose it in a sum of uneven functions, right? And sines are indeed uneven functions. So this is why here we have really a sum of sines. Here I have continued to play with the sliders, and what appears now is a function that looks like a triangular waveform, right? And this suggests again that if you would take more terms, you would have an approximation that would be even more precise. Again, in our sum we only have uneven harmonics, as you can see over here. The even harmonics are all zeros. As you can see here, the trigonometric functions that are appearing in our sum are all cosines. This you can see over here as well, because our phase shifts are 0. This makes sense because a triangular waveform is an even function, and it makes sense that if you're trying to approximate it, you would obtain a sum of even functions, and cosines are indeed even functions. Since it's so much fun, I've continued playing with the sliders, and look what has appeared, something that looks like a sawtooth wave. Again, if you would take more and more terms in the approximation, you would be able to improve on your approximation. As you can see now, all harmonics are present in the signal. Since the sawtooth wave is an uneven function, we expect a sum of sines, because sines are uneven functions, and this is indeed the case. What you can see over here, that this is a sine and this is also a sine, but it's multiplied by -1. So you have alternating signs in the amplitude over here. So you can see here indeed harmonic 1, so the fundamental is a sine, and this is, well, minus a sine. This is the second harmonic, and you can kind of see this alternation of signs here in the picture. It appears from this animation that you should be able to approximate any periodic function using a sum of shifted cosines, as we have done. Of course, as you imagine, I did not play with the sliders to produce a square wave, a triangular wave, and a sawtooth wave. I've used a systematic way, in the sense that I've computed the Fourier coefficients for each type of wave. And this is what we'll consider now. Well, this first animation suggested that you could probably decompose any periodic function f of t by not considering 7 terms in the sum, but by considering an infinite number of terms. But is this really so? If you look at the literature, as often the answer is yes, but. A first condition is that the function f of t must be absolutely integrable over a period, which means that if you take the absolute value of f of t and you integrate it over a period, well, this integral must be bounded. There are two other more technical conditions which I will not discuss in this video, but together with the first condition, they form the so-called Dirichlet conditions. It suffices to know that most functions used in engineering problems have a Fourier series like the one that is shown here on the screen. Now that we know that most periodic functions used in practice have indeed a Fourier series, the natural question that arises is, of course, the computation of these Fourier coefficients. Before we continue, I'll introduce two alternative expressions for the Fourier series decomposition. For that, I will introduce the so-called complex exponential e to the g omega 0 t, which is really a complex valued function. Its real part is a cosine and its imaginary part is a sine. This is something that you have encountered previously, and if you plot this in the complex plane, it looks like a rotating vector rotating counterclockwise. What we'll do in this expression is replace the cosine by an expression that involves this complex exponential. There are two ways to do this. Here is the first way, the most obvious way maybe. Of course, the cosine here can be written as the real part of this complex exponential. A second way to do this is as follows. What you do, and this is true for any complex number, well, you take the complex number, right? We want to obtain the real part. You add its complex conjugate, here it is, right? If you add these two, well, the imaginary parts will cancel out and you'll have 2 times the real part. So you'll have to divide by 2 or multiply by 0.5. Well, before we continue, let's have a look at two animations that kind of illustrate these two expressions. Well, you can see the rotating vector in blue. As you can see, it's rotating counterclockwise. Remember that we consider a period centered around t is equal to 0, so we consider times going from minus t over 2 to t over 2. The corresponding arguments of the rotating vector are at the start minus pi and at the end pi. And as you can see, the cosine is the real part of the rotating vector. Well, notice that you have now two rotating vectors, one rotating counterclockwise and one rotating clockwise, and they both have amplitude 0.5. we can again look at the starting and ending arguments of these two rotating vectors. The one rotating counterclockwise starts at minus pi and ends at pi, whereas the one that is rotating clockwise starts at pi and ends at minus pi. As you can see, the vector sum of these two rotating vectors produces here a cosine. The expression of the Fourier series that you see here on the screen is the one that we've used in animation 1, and the idea is now to come up with an expression that uses phasors, right, rotating vectors, and we'll first use this expression here involving the real part of this phasor to produce a cosine. Going from this expression to this expression is really a straightforward application of the formula. Well, this modulus of ck is a real number, so what you can do is take the real part and put it in front of the sum, and this is how you obtain this expression here. And also, by the way, what we have used is the property of the exponential, that the exponential of a plus b is the exponential of a times the exponential of b. So this is how we go from this expression here to this expression times this expression. And the reason we do this is that we see here that we have ck appearing. And this is how we end up with a third expression of the Fourier series. And later on in the video, I will give you a nice interpretation of this using an animation. Well, let us start again with our second formulation of the Fourier series, and this time we'll produce a formula that is sometimes called the exponential form of the Fourier series. We'll now use the expression that is at the basis of animation 3. Remember that the cosine is constructed from two phases, one rotating clockwise and the other one rotating counterclockwise. Well, I did not mention this before, but this formula is sometimes called Euler's formula. And if you use this formula, well, you can go from this expression to this expression. So this is really a straightforward application of the formula. So to go to the next expression, we'll use again this property of the exponential to rewrite this one and to rewrite this one. So this is the exponential of j times the argument of ck times the exponential of jk omega 0 t. And here you have the same thing but with minus signs, right? So exponential of minus j argument of ck times the exponential of minus jk omega 0 t. If you take this one times this one, this is really ck, right? And this one times this one, this is ck conjugate. And this one, you find it over here, and this one, you'll find it over here. So to go to the next expression, we observe here that we have minus k, and here is ck conjugate. We would like to have an expression where you have minus k, and in here we have minus k as well. So simply we are going to rename this one as c minus k, right? So we have minus k here and minus k over here. Of course, when we'll have a way of computing ck, we'll have to check that ck conjugate is indeed equal to c minus k, but this is a problem for later. To obtain the next expression, what we would like is to obtain the same expression in the summations, right? And you can do this very easily by considering here a change of sign, right? And this is why we have now a summation from minus infinity to minus 1. And this is how you obtain the final expression, right? Notice that we cover all indices from minus infinity to minus 1. We cover the index 0 and then indices 1 to infinity. So this is how you can write this under this form. Notice that this is correct also for index 0, because if you plug in k is equal to 0, since the exponential of 0 is 1, you obtain indeed this term here to be C0. Well, we still have to look at the fact that we have a coefficient 2 appearing in the three first equivalent expressions of the Fourier series. Well, this comes from the fact that the ck's are derived from a formula that is based on this description, right? This description is the exponential form of the Fourier series. We'll see how to calculate the ck's very soon. But if you look at this sum here and you consider, for instance, a positive index k, right? Well, you'll have here related to this positive index k a phasor that is turning counterclockwise, right? But in the sum you'll also have the opposite index minus k, and this will produce, right, a phasor turning clockwise, right? And we can now use Euler's formula that I have rewritten very slightly. And if you add these two phasors, right, you have 2 times a cosine, and here you have the factor 2 appearing. So this is a summary of what we have obtained so far, right? We have 2 expressions here of the Fourier coefficients, 1 expression here under a polar form, and 1 expression here under a Cartesian form. Notice that we still haven't found a way of computing the Fourier coefficients, but we'll do this pretty soon. And then we have 4 different ways of writing the Fourier series, and they are all equivalent, but of course the interpretation is different. The interpretation of this expression here is that we decompose f of t into a sum involving sines and cosines of increasing frequencies, right? We start with the fundamental frequency, k is equal to 1, and then we consider the harmonics, with k being an increasing integer. Well, with this second expression we have something quite similar, except that we work only with cosines, but with cosines that are shifted over here. And this expression is at the basis of this first animation that we saw at the beginning of this video. Well, the 2 most recent expressions of the Fourier series involve phasors, and later on in the video I will show you some animations that will give you an interpretation of these 2 formulae. Well, in this expression over here you have for each harmonic, and of course for the fundamental, 1 phasor turning counterclockwise. So the animation that I will show to illustrate this formula here will be a kind of generalization of what we have seen in animation 2. Well, when you look at this formula over here, you can see that for each harmonic there is a phasor that is turning clockwise. That's for the positive index, but related to that is the opposite index, and that will generate a phasor that is turning clockwise, right? So when you'll see the animation that is kind of an interpretation of this formula, you'll have to make the link with animation 3. We'll see later in the video that this formula is at the basis of the so-called trigonometric Fourier series, and that this formula is really the exponential form of the Fourier series. And finally, it's time to go for the computation of the Fourier coefficients, and to do that we'll use the exponential form of the Fourier series that you can also write like so. So let us have a look at this function, and in here we have this parameter c0, and in the first animation we have used this c0 to kind of shift the function, right? So this c0 must be the average of the function over a period. So let's have a look at the integral of this function here over a period t. So this is the integral over a period of f of t dt. It will be, of course, a sum of integrals of functions like this one, right? So let's have a look at the integral over a period of c minus 1 exponential of minus j omega 0 t d of t. right? So this one over here, well, it's constructed from a cosine and the real part and a sine in the imaginary part. But if you integrate a cosine and a sine over a period, of course, what you have is 0. So all those terms like this one over here will be 0, right? It will also be the case for the integral over a period of this function, and so on, right? So there will be one non-zero contribution, and it will be the integral over a period of this constant. And this obviously will simply be C0 times t, right? So instead of writing the t over here, I'll bring it to the other side, right? So then you have 1 over t over here. And as we had expected, C0 is the average of the function over a period. We'll use a very similar idea to compute the other Fourier coefficients. So imagine we want to compute C2 over here. What we'll do to have in this sum C2 appearing without an exponential, well, we'll multiply the whole expression by the exponential of minus j2 omega 0 t, right? And in this way, C2 will appear alone. And if we do this, indeed, this is what we obtain, right? C2 appears here without an exponential. So now we can use the same trick. Indeed, we integrate the function over a period t. We obtain again a sum of integrals over a period of, well, the different terms, right? These terms will all be 0, right? Except one, and it's precisely the one where there is no exponential appearing, right? So here we'll have simply C2 times t. So this is what you see over here, and I can bring, of course, the t on the other side. So C2 will be the average over a period of the function here that you see appearing, f of t times the exponential of minus j2 omega 0 t, right? We have done this for C2, but we can do this for any coefficient, Fourier coefficient. So in general, for ck, this is the expression that we are going to obtain. Remember that we had used the fact that ck conjugate is equal to c minus k. Let's have a look if this is the case for this expression here of the Fourier coefficients. Remember that f of t is a real valued function. If you take the conjugate of ck, what will change over here, instead of minus j, you'll have j, right? And you can see that this is also equal to c minus k. If k changes sign, well, instead of minus k, you have k. So indeed, ck conjugate is c minus k. Well, in summary, if you look at the exponential form of the Fourier series, well, you'll find this expression here, right? And the ck's and the Fourier coefficients are obtained using this expression, right? And C0, as you can see, is simply the average of f of t over any period. Well, if you look at the literature, you will also find the trigonometric Fourier series, which looks a bit different, but if you look at it more closely, well, it's closely related, of course, to the exponential form of the Fourier series. So what we'll use now is this equivalent expression of the Fourier series, right? Remember that these are the Fourier coefficients, right? And since this is a real valued function, what you can do is we'll kind of look at the real part of ck. Here it is, right? Because this is, and if you take the real part of this one, you have the cosine of k omega 0 t, right? And then you have the imaginary part with a sign, and because of the minus sign over here, you have minus over here, right? So here real part, and here imaginary part. And so what you can do now is plug this in here, right? You have a minus sign here and a minus sign here, right? So they will cancel out and you'll have a plus sign. So what you can do, right, is write this with, well, this is how usually it is written, with a0 over here. A0 will be simply the average of the function over a period. You'll write here a of k, and a of k will be this expression here multiplied by 2, right? And you can write plus bk times a sine, right? And this bk will be this expression over here times 2. And this is what we see on this slide. So if you look at the literature and you look for the trigonometric Fourier series, you'll find expressions very close to this one. After all this hard work, we have deserved an animation to kind of explain all the concepts visually. We will use the second expression of the Fourier series, the one that involves shifted cosines. And then of course we'll need the expression that allows us to compute the Fourier coefficient, and you have to see this as the average over a period of the function that you're decomposing times a complex exponential, right, at the, well, related harmonic k, and of course here you have a minus sign appearing. And of course you can rewrite this expression like so. We know that f of t is real valued, so the real part of this one will be a cosine, okay, that's what you see over here, and the imaginary part will be minus a sine, right? So the real part is of ck is really the average over a period, and it's the function times a cosine at the harmonic k here, right? And you have something similar for the imaginary part, except here that you have the minus sign. So here's animation 4, and as you can see, well, I've used Python and the Anaconda environment to program this animation. Anaconda and well, Python is really a nice environment if you want to do those kind of things. I encourage you to discover this Anaconda environment, and why not reprogramming this animation. You'll learn a lot about Python and also the Fourier series. Well, as you can see, we're working with a signal that is a sawtooth signal, and it's the signal here in blue. And what we have done is, well, compute the Fourier series expansion, right? And here we are only showing 7 terms. So we consider the fundamental, right? And also harmonics 2 to 7. Well, let us start with the computation of the first Fourier coefficient. Remember that to compute the Fourier coefficients, we have to consider f of t and multiply by the exponential of minus jk omega 0 t. Here k is equal to 1. If you look at this function in the complex plane, this is what you obtain for k is equal to 1. So what you have here is the real part, and here you have the imaginary part. What you can do now is kind of take the real part, which is the function times the cosine k omega 0 t, k is equal to 1 here, and well, look at it as a function of time. Here we have a function that is periodic of period t. Now remember that we consider periods that are centered around 0, right? And here we have this real part here as a function of time. In the background, what you see, well, you see the cosine, and this is this one over here, and here in red you see the function, the sawtooth. If you multiply both, this is what you have, right? And if you take the average over time here, you can see that it's 0, right? So here the real part of C1 is 0. You can do something very similar for the imaginary part, but remember here we have this minus sign, right? So here again in red you have the function, right? Here you have minus sine omega 0 t. Here you have the product of both, and then you take the average over a period, and here you obtain that the imaginary part of C1 is minus 0.32. Of course, I didn't tell you before, but the integration, also the calculation of the average over a period, is done in the background, and the integration is done numerically. The real part of C1 is 0, the imaginary part is minus 0.32, so C1 being a complex number, you can represent it here in the complex plane. If you remember this first expression of the Fourier series, the one in terms of cosines and sines, you'll remember that, well, the real part is related to the presence of a cosine here at the fundamental. There is none, right, because the real part is 0, but there must be a sine at the fundamental frequency, and in this formula we had to take the imaginary part and multiply by -2, which explains here the presence of a sine at an amplitude of 0.64. Well, you can also work with a polar expression of C1, right? Obviously, well, the modulus will be 0.32, and since, well, the real part is 0 and the imaginary part is negative, well, you'll have a, well, argument of minus pi over 2, right? And the reason why we like to work like this is that you can represent this in a so-called line spectrum. So here you see the indices k, right? K is equal to 1 is the fundamental frequency, and then if k increases, well, you have harmonic 2, 3, and so on, right? So what you see here represented is, in this graph over here, the modulus of ck, and here the argument of ck, right? And we have just computed it. The modulus is 0.32, you can see it over here, and the argument is minus pi over 2, right? So what is the interpretation of that? Well, for that you have to use this second expression here of the Fourier series. You have the decomposition of the function in terms of the mean and the average of the function over a period, and then a sum in terms of shifted cosines, right? And then for the amplitude, you have to take the modulus that you read in this graph over here times 2, right? And then you have to take a cosine with a phase shift. And here a phase shift of minus pi over 2 means that the cosine will become a sine, right? So at the fundamental, you'll have a term here with an amplitude of 0.64, right? And you'll have a sine omega 0 t because of this phase shift of minus pi over 2. And again, this is what you see over here in the decomposition. What we have done for the fundamental frequency, we can do for the second harmonic. So here you have the computation of C2, right? So here you have the function times the exponential of minus 2 times j omega 0 t, right? Here you have the real part, so it's the function times cosine 2 omega 0 t, and here you have the imaginary part, something similar, but you have a sine here and a minus sign, right? So here you have the real part and the imaginary part as a function of time, right? We still have the function here in red, okay? Here you have the cosine 2 omega 0 t, and here minus the sine omega 0 t. If you multiply, you have the function in blue, right? And then again you take the average over a period. So here again we have 0, and the imaginary part is positive now, right? So we have here a complex number that is shown over here. We have the modulus over here, and the phase shift is now plus pi over 2, and this is indeed what you see here in the line spectrum. So if we take this interpretation of the Fourier series, we'll have a cosine that is phase shifted by plus pi over 2. So this is a sine multiplied by minus 1. And the amplitude, you can read it over here. So it's 0.16 times 2, 0.32. And here it is, right? So this is the second harmonic in the decomposition of the Fourier series of this sawtooth function. Well, what we have done for the fundamental frequency and for the second harmonic, you can do for all harmonics. In this case here, I have stopped the computation at the seventh harmonic. By the way, look at the pictures that you produce by considering the function and multiplying it by the exponential of minus jk omega 0 t. I will not go over the details again, for instance, for the computation of C7, because the ideas are exactly the same as for the fundamental frequency and the second harmonic. What is really important is the interpretation of the line spectrum. So if you're looking, for instance, at the fifth harmonic and its contribution, you can read it from the line spectrum. Here you have the phase shift, minus pi over 2. So the cosine will become a sine, so you'll have sine 5 times omega 0 t, and the amplitude, well, you can read it over here, and you have to multiply by 2, right? And you can read it over here, it's a sine, so it's this one over here. Of course, the same kind of ideas are valid for other waveforms. Here you have the square waveform and the computation of the Fourier coefficients. And here you have the Fourier series decomposition for a triangular wave with its corresponding line spectrum and the computation of the Fourier coefficients. Well, the nice thing about the Anaconda environment and Python is that you can play with sliders. Here the function has been constructed using these sliders. You can see the shape here of the triangular function, right? And then you can see what happens if the function changes. For instance, if I change the amplitude over here, it takes a while for the computation to act, but you can see that the Fourier series adapts, and so is of course the line spectrum and the computation of the Fourier coefficients, right? So this is something you can explore in Anaconda Python. In the next animation, we'll have a look at the third interpretation of the Fourier series that you see here on the screen. And here you can see that for every harmonic, starting from k is equal to 1, so that's the fundamental, to increasing harmonics, well, we have one rotating vector, right? And then we take the real part, and this is kind of a generalization of what we saw in animation 2, where we generated the cosine as the real part of a rotating vector. In this particular case, we'll consider a square wave. You can see from the line spectrum that there will be contributions only at the fundamental and at harmonics 3, 5, and 7, so the odd harmonics. You can see the fundamental in green, harmonic 3 in cyan, harmonic 5 in yellow, and harmonic 7 in blue. Of course, here we'll consider vector sum, so the fundamental frequency will be a rotating vector that will turn around the origin, whereas the rotating vector that will correspond to the third harmonic will rotate, but its rotating point will be at the end of the rotating vector corresponding to the fundamental frequency, and we'll continue like that with the rotating vectors corresponding to harmonic 5 and 7. In this animation, we'll consider a period of the function and a period centered around t is equal to 0. So time will go from minus t over 2, t is the period, to t over 2, and corresponding to that there will be an argument of the given rotating vector, right, theta k, that will go from minus k pi plus argument of ck to k pi plus argument of ck. So for instance, if you take the third harmonic, the starting argument will be minus 3 pi minus pi over 2, and at the end you'll have an argument of 3 pi minus pi over 2. So this rotating vector will do a full rotation 3 times. If you take harmonic 5, it will have 5 full rotations, and so on. And let us now have a look at the animation. Notice that we're only interested in the signal in green, that's the real part. The imaginary part, so the signal in red, is only a byproduct and it's of no interest to us. And here you have the same kind of animation, but for a triangular wave. And for a sawtooth wave. And we have now arrived at the sixth and last animation. For that we'll use the standard form of the Fourier series, so the exponential form. In this sum, for a given harmonic k, well, you have a positive index and a negative index, right? So the positive index will yield a rotating vector turning counterclockwise, and its counterpart, that is negative, will give you a rotating vector that is turning clockwise. So this is kind of a generalization of what we saw for the cosine in the animation 3, where we used, well, Euler's formula. In this animation we take the exponential form of the Fourier series and we decompose it in three main terms. So C0, that's the average of the function over a period, in our case 0, and then two main terms, one corresponding to the positive indices and one corresponding to the negative indices. Notice that in the term that corresponds to the negative indices we have taken a sum from 1 to 7, but in the complex exponential we have taken minus k instead of k, and instead of writing c minus k we have taken c conjugate. Remember that c conjugate, ck conjugate, is c minus k. In this way we see that there is a sum where we have collected the positive indices and we have an exponential with k indices, and that will be, well, a sum of rotating vectors turning counterclockwise, and in the other sum, because we have an exponential of minus jk omega 0 t, we'll have a sum of rotating vectors that will be turning clockwise, right? And if we take the sum of both terms, and in the animation it will be the vector sum, will be producing the signal that we have decomposed, and this is what you'll see in green. Notice that in this last interpretation the vector difference, which is shown here in red, will always be 0. This will always be the case if you decompose a real valued function. Notice that in the line spectrum we have also shown the indices that are negative, right? But remember that c minus k is ck conjugate, right? So this means that in the line spectrum, well, you have the amplitude line spectrum, so that's the top part of the line spectrum, that is even, and you have, well, the second part of the line spectrum that is corresponding to the argument of ck, that is uneven, right? So basically this is why we usually show the line spectrum only for positive indices. Let us now have a look at the animation for a square wave. And of course we can do the same type of exercise for a triangular wave. And for a sawtooth wave. Well, this concludes this video on the Fourier series. If you liked it, don't hesitate to push the like button and to subscribe to this channel. See you very soon for a next video on this channel.